All right, we're going to go ahead and forge ahead. This is chapter number 6. If you're using the Brown and LeMay textbook, this is chapter number 8. If you are using the Interactive General Chemistry textbook, all this is about basically the electronic structure of atoms and kind of spatial arrangement of all the different subatomic particles. Now, in order to get into this, what we first have to do is we need to address light. Light is kind of complicated and maybe even a little bit tricky because of the fact that it behaves in two different manners. If you send it through a prism, like a light prism, think the cover of the Pink Floyd Dark Side of the Moon album, or album cover, it behaves as a wave, and you see this entire visible light spectrum down here. So I'm going to go ahead and draw a little, that visible light spectrum is something that you'd see. Now, light also behaves like a small stream of particles, and that is best represented through what is known as the photoelectric effect. If you send low energy light towards a metal surface, well, electrons are going to be ejected from that metal surface, whereas if you send high energy light at that same metal surface, well, higher energy electrons are going to be ejected from that surface. Now, these different visible lights, when you think about it from a prism, these different visible lights are forms of electromagnetic radiation. This is the type of radiation that is visible to us, so that's why this is known as the visible region. This radiation falls within the, quote, visible region of the electromagnetic radiation spectrum. Now, the wave-like movement of a light is something that we need to consider, and that is radiant energy, and it moves at a constant speed, which that constant speed is generally denoted as c. I'm going to put parentheses around that. C is the identifier for the speed of light, which is 3.00 times 10 to the 8th meters per second. So that's 3,000,000,000. That's 1, 2, 3, 4, 5, 6, 7, 8. 3 times 10 to the 8th meters per second. Now, there are several characteristics of a wave that you need to understand in order to, in addition to that constant, and that constant speed, you need to know what a wavelength is. And this is identified by this symbol right here, lambda. So wavelength is the distance between two different peaks. So if you look at something like this, what I've got a star by at the bottom here, a wavelength is from peak to peak, or you could look at it as trough to trough. So that is one entire wavelength. That right here, this, I'm going to go ahead and change color and do it blue. So from that blue spot to that blue spot is one wave length. So now that we've established what a wavelength is, we need to draw a correlation between, a connection between wavelength and frequency. Now, the relationship between wavelength, frequency, and speed is best represented through this equation. C is equal to lambda times v. Now, this v is a little bit tricky because this is not v as in velocity, but this is v as in mu, so it's actually that symbol right there. And that symbol right there is frequency. Now, when we expand upon that exact equation, we have c is equal to speed of light, wavelength, which is lambda, and this v symbol for frequency. What I want to do is I want to write out these units. So speed of light is going to be measured in meters per second. That's a constant. Lambda, wavelength, is measured in meters, and frequency is events per second, or it's simply written as SEC to the -1 power. This is also written as hertz, and if you use a computer or something like that, you know, well, it used to be megahertz is the speed for your computer. But anyway, that's something to consider. So now, with that said, I've got three different models right here. I've got model 2 and model 3. Those are the ones that I want to compare. And what I want to compare about those is, well, what are my wavelengths? And what is the difference between these wavelengths? So if you look at this, where I'm drawing a line from here from these two x's that I'm drawing, imagine that is a measured time frame. So what we've got is basically in figure number 2, we've got a certain number of wavelengths that are being completed. So what I'm going to do is I'm drawing an X on figure number 2 and then another one to indicate 1 completed wavelength, another line to say 2 completed wavelengths, 3 completed wavelengths, 4 completed wavelengths. So I've got 4.5 lambdas that are completed in that time frame. Now, if I look at figure number 3, in the exact same window of time, looking at my x-axis basically as a time frame, well, that's 1 completed wavelength to a half, so 1.5 wavelengths. So what's the difference between these lambdas? Well, figure 2 is a short lambda, and figure 3 we've got a long wavelength, a long lambda. Okay, now if we go on from there, one of the things that you want to consider is how does that relate to my electromagnetic spectrum, which I'm bringing up at the bottom of this slide. Okay, so the visible region of this ranges from 400 to 750 nanometers. So what I have is a range is the visible spectrum from 400 to 750 nanometers. What I always like to do with that spectrum is I like to think about the units that I'm talking about there. 400 nanometers, I want to go ahead and convert that on the fly to meters. And so I've got this 4.00 times 10 to the negative 7th meters. So 400 nanometers is equal to 4.00 times 10 to the negative 7th meters. Now, if I compare that to 750 nanometers, that's 750 is 7.50 times 10 to the negative 7th meters. Now, when you compare those two, well, a 400 nanometer wavelength compared to a 750 nanometer wavelength, which one of them is going to be considered a longer wavelength and therefore would have a lower frequency? So that 750 nanometer wavelength is longer, so this one over here is going to be a lower frequency. The 400 nanometers, that's going to be, well, that's going to be a higher frequency, and that is also going to be a longer wavelength. Or I'm sorry, a shorter wavelength. So shorter wavelength is going to be equal to a high frequency, and a long wavelength is equal to lower frequency. Okay, so once you have all of this, it's important to have a good understanding and appreciation for this equation right here and the different variables that are there. I also highly recommend being able to do this conversion, this 750 nanometers, or I'm sorry, this 400 nanometers to meters pretty easily and pretty quickly. If you can do that, that's going to save you a lot of time on a practice problem. So then you don't have to do, or on an exam, so then you don't have to do those sorts of conversions. Now, changing gears a little bit, we're back to the atomic structure. Our atomic structure is basically this model that is over here on the right-hand side of the slide. We've got a nucleus in the center, we've got protons and neutrons found within that nucleus, and then outside of that we've got these electrons. These electrons are floating outside of this. This is our nuclear model. This has protons and neutrons in the center, and electrons are, well, they're out there as well. Or they are distant from the nucleus. Okay, now with respect to those different subatomic particles, we've already talked about them from the context of what are their charges. The protons are positively charged, neutrons have no charge. The masses of those two different things, well, basically all of the mass of an atom is found within the nucleus, and all of that mass is directly connected to the protons and neutrons. Electrons, on the other hand, well, they have a negative charge, and they basically have no mass whatsoever, or they have a relatively insignificant amount of mass. Now, one thing that I'd like to draw your attention to is this slide right here, or sorry, this figure right here. What this figure shows is what is known as a cathode ray tube. And it's this cathode ray tube experiment that basically helped elucidate that electrons had that negative charge. And what this experiment consisted of was sending an electric current through a gas and causing a beam of electrons to basically shoot from a negative charged an anode to a cathode. Now, what you see here, and I'm circling this hand with a magnet on it. Now, I gotta apologize, and I gotta go ahead and erase that circle there, because inside this small tube, or inside this chamber, there's this green light in this line that reflects, or that basically appears to be your negatively charged electrons, or that beam of electrons. Well, that beam tends to be going toward those magnets, or that magnet. And so what that gave away was this idea that, well, electrons have a little bit of a charge to it, and they can be influenced by the presence of a magnet. Now, if you are using the interactive general chemistry textbook and you look on page, I believe it's 84 of your textbook, let me make sure, sorry, 85. This shows the cathode ray tube experiment in a little bit more detail, and that electron beam moving and everything like that. So after the cathode ray tube, I need to introduce a pair of people. This is Joseph John Thompson. JJ to his friends. This is Niels Bohr. Okay, so what's significant about these two individuals, J.J. Thompson here, he did the cathode ray tube experiments. I call those the CRT experiments. Okay, and he was basically awarded the Nobel Prize in physics. And he was more or less credited with identifying the electron. You know, that was just fantastic. This is wonderful. People have been wondering, what are these different subatomic particles? And J.J. Thompson was like, I got this experiment, this cathode ray tube experiment, and what I'm going to show you is that there's the subatomic particle that's got this negative charge. I'm going to call it an electron. Now, Niels Bohr was a little bit younger than J.J. Thompson. And at some point in Niels Bohr's scientific career, he said, you know what, I need to go talk to J.J. Thompson. J.J. Thompson's the guy who basically came up with an electron. And I've got some ideas about electrons. And I've got this idea that electrons live around a nucleus and they're in discrete levels. So electrons exist in discrete levels. Levels. So almost like we've got this idea of here's our nucleus, and then some electrons are going to live there, some electrons are going to live there in this Nick shell, and then some electrons are going to be living out there. And those aren't very well drawn circles, but that's what they're supposed to be. Now, J.J. Thompson's experiments had been, well, I'm going to send an electric current through a gaseous sample, and I'm going to see what happens. And lo and behold, I'm right, I'm awesome, this is fantastic. Niels Bohr, on the other hand, was like, what if we heated these gases? What would happen? And Niels Bohr's experiments largely gave us the following. So Niels Bohr said, let's think outside the box. Let's take some hydrogen gas and heat it up. Now, what's actually going to be produced? When we heat that hydrogen gas, what we're going to see are 1, 2, 3, 4 different lights. That's pretty neat. Okay, so this is pretty cool. We've got these 4 discrete lights. And what was Niels Bohr's hypothesis? Niels Bohr's hypothesis was that electrons lived in discrete levels. And so we have these four discrete colors, these four discrete wavelengths. So the specific wavelengths aren't particularly important at this point, but what does that actually mean? And Niels Bohr's idea was that, well, this was an indication that these electrons lived in or could be in discrete levels. Now, as we mentioned previously, when we talk about wave-like characteristics of something, we don't talk about the speed of radiant energy. It's always the speed of light. Instead, we talk about the frequency of waves. And we previously kind of concluded that the higher the frequency, the shorter the wavelength. And we were talking about wavelengths of light. Shorter wavelength, something like violet compared to red, was a much longer wavelength. And so we saw these connections between wavelengths and frequencies. So the work done by Niels Bohr gave us this connection between ultimately energy and the frequency of light. Okay, so E is going to be the energy of a photon. Our units for measurement of energy are going to be J, or joules. We've talked about joules previously. The next component, or the next player in this equation, H, is going to be Planck's constant. That is 6.626 times 10 to the negative 34th. That's a constant. I'm going to give you that on exams and everything like that moving forward. But then this last variable, V, that's one that we've actually seen before. That is going to be our frequency. Let's think about these units. What are the units for frequency? Well, those are inverse seconds. -1, which that is equal to 1 over seconds. Okay, so then let's think about Planck's constant. If we multiply frequency times Planck's constant times joules times seconds, well, seconds are going to cancel out, in which case we're going to be left with joules. Now, to see all that, so with this practice problem, and so this practice problem right here is one type of sunburn occurs on exposure to wavelength, or to UV light of wavelength in the vicinity of 325 nanometers. I'm going to highlight that because I know that I'm going to use that number. What is the energy of a photon of this wavelength? So I'm going to be looking for energy. And whenever I think of energy and I'm relating that to wavelength, what I want to do is I want to think about those two equations. One of those equations is E equals hv. Okay, E is my energy, H is my Planck's constant, which that's 6.626 times 10 to the negative 34th joule seconds. What I'm trying to figure out is, well, after it's all said and done, is I'm trying to figure out that value right there. Okay, now I need to get basically frequency. All that I'm provided is my wavelength. So now what I know that I need to do is I need to use my other equation, which is C equals lambda times frequency. And my frequency, my V there, well, that's what I'm solving for. So I'm going to rearrange this equation. C over lambda equals frequency. Okay, do I know my C value? Yes, I do. That's the speed of light. It is always 3.00 times 10 to the 8th meters per second. My lambda is 325 nanometers. If I'm talking about 325 nanometers, I can go ahead and write that as 3.25 times 10 to the negative 7th meters. So 3.25 times 10 to the negative 7th meters. And that is equal to frequency, my V value there. When I have that V value, which this V value ends up being 9.23 times 10 to the positive 14th inverse seconds, well, then you can plug that into this equation. Plug this into right there, because we have that Planck's constant. So E is equal to 6.626 times 10 to the negative 34th joule per second, or joule second, sorry, not joules per second, times 9.23 times 10 to the positive 14th inverse seconds. Whenever you plug those two numbers in, multiplying by one another, what you get is maybe a little bit alarming. Times 10 to the, just a second, exponent to the negative 34th. What you get is 6.12 times 10 to the negative 19th joules. That's negative 19. Now this is a little bit tricky, and one of the toughest parts about these sorts of problems when you're talking about the energy of a single photon is you get these numbers that are like crazy small, times 10 to the negative 19th. How do you even know if that's right? One way that you can look at it is you're thinking about a single photon of light. So you're not talking about, you know, streaming light at something for 4 hours or anything like that, or for whatever extended period of time. You're talking about one single photon of light. So if you see something that is times 10 to the negative 19th or something, don't be alarmed by that. That is probably the right answer. In this case, that is the right answer. All right, well, I hope this was helpful. Have a good afternoon.